Right. Last class we discussed about the Grignard's reagent. Now let's see a few simple questions in here. For example, magnesium is treated with this one. So what is the product that you will get? See, in simple terms. First, you would get NH, and then you will get minus here and MgBr here. Okay. But the problem is internally there will be shift of that proton because the hydrogen here on that nitrogen is acidic, so that will go all the way and then you'll get mgbr. So this is the X product that you should report, and then this X product is treated with HC double bond O, H in acidic medium. So in acidic medium you will get this one. Sorry, it's not acidic medium directly. First, this negative charge would go attack here, bond would open up, so we would get nitrogen connected to carbon with CH2O minus, and that on hydrolysis will take up the H plus, thus giving you alcohol here like this. So this is product Y that you need to report. Okay, so this is X, this is Y product. Next thing, if you have H3O plus added onto this, so I mean CH3MgCl added onto this, first step would be attack on this nucleophilic position. So we would get like this with O minus and CH3 getting connected here. So with MgBr plus, this is the first equivalent. Now when you add the second equivalent, that is CH3 MgBr, again attacking on this carbon here, so this bond will break on this, so we will get O minus MgBr plus, and then we have O minus MgBr plus, and the other product will be C double bond O, this one. Again, one more mole of CH3 MgBr will attack, and this time it will attack on this position, so that will lead to formation of tertiary butoxide with Mg plus and Br minus, which on hydrolysis eventually lead to formation of this alcohol. Okay, and in fact the other alcohol on hydrolysis which you will get is from this one, so which will have 3 carbon here, 1 2 3 carbon with alcohols this way. This is a product formation. Okay, I suppose all of you understood that point. So it is like a diester form. So total number of moles that we have used here, so first mole in CH3 MgBr, this is the first mole which I have used here. So let me mark that. This is the first equivalent, second equivalent, third equivalent. So after the third equivalent, we will eventually get the alcohol form. Okay. Next. In case if you have CH3 MgBr in excess, one side there is an ester form, one side there is an acid chloride form. Reactivity wise, if you remember, the acid chloride is more reactive. So first the attack would be on this end, that makes it CH3 double bond O, O ethyl. Again, the next mole of CH3 MgBr will be attacking on this end. This time this bond will break. That will make it CH3, C double bond O, CH3. And then again the third mole, CH3 MgBr, will attack. So again you will get eventually, after hydrolysis, you will get this as tertiary alcohol. So here also you will notice that 3 moles have been used. First mole, second mole and third mole. So after 3 moles you will get this product. Next, if left hand side and right hand side of a ketone are extremely bulkier, in the sense we have tert-butyl or this kind of dimethyl and ortho-dimethyl, benzene forms, then it is very, very difficult to make any RMGX reaction on this one. So here we can say there is no reaction of RMGX. By chance, if you have dicyanates connected, in such case, RMGX will try to connect on one carbon, removing the other carbon as Cn minus. That's how you will get RCN. And RCN, if you attack, I mean, if the number of moles given are in excess, then this RMGX will again attack on carbon here, correct? And that will convert this into RCR with double bond N minus MgX plus, and that on hydrolysis will give you ketone. So you will end up answering at ketone. A lot of students would ask, sir, why not we are doing further reduction of ketone into alcohol? Problem is the minute when you hydrolyze it, there is no more RMGX left. Everything of RMGX will convert into RH. So in case if I take excess amount of RMGX, it will convert it to RH, and that is the end of it. Just like how we have reacted RMGX with carbon dioxide, the same type of reaction happens here also, where R minus connect to SO2. You will get this as RSOO minus, and then hydrolysis you will get alkyl sulfurous acid. Next, when it comes to CH3MgBr, if you have to decide between an acid-base reaction or a nucleophilic attack, the first preference is always to acid-base reaction. This is the first preference. The second preference is always towards the nucleophilic attack. So since there is only one equivalent taken, so you always make this as the reaction. So this plus CH4 as the product. If at all we have two equivalents, first you will get this, second you will get this, O minus and MgBr here. Like this, you will have this as O minus and MgBr plus. And then on hydrolysis, both sides you will again gain into an alcohol form. Okay. Next, CH3MgBr here will first take H plus. Since it is excess, it will again take H plus from here. It would create what we call it as C triple bond C minus and minus here. And this with MgBr plus here. And the other side also MgBr plus here. And when you treat that with 2 moles of aldehyde, one aldehyde on this end and one aldehyde on the other end here, so I can say this C minus can go connect onto carbon, this C minus can go connect onto this carbon. So we will get this as an alcohol form here with this carbon, and that is connected to a carbon which is triple bonded. Once again, this one only, carbon with triple bonded, and this again is connected to another carbon which is alcohol, right? So this is a final product that you need to report. In a similar style here also you can see CH3, when you connect onto this ester form, first this bond will break and you would get this carboxylate on one side and ketone on the other side. Second mole, when it comes to second mole, this CH3 again connects onto this position. You will get an alkoxide on one side, carboxylate on the other side. On hydrolysis, you will get alcohol and acid on the other side. Okay, so you'll have this as the acid C double bond O and OH form. This is a product formation. Next, in case if you have one equivalent of CH3MgBl here, so first reaction would be always about attacking the uh, highly strained three-membered ring here, opening up this oxygen to get O minus. And once you get that O minus internally will attack again, removing Cl minus. So that gives you this product. In case if you have four-membered ring also, the same nature you will do it here. So CH3 will attack onto this position, bond will open up, and then you will get this O minus. On hydrolysis, you will get this alcohol product. Correct? So these are very standard reactions that you need to learn from Grignard's reagent. Okay. The last one being, in case if you have, uh, ethyl carboxylate here, correct? So in this case, we have OET, OET, OET all connected with RMGX. So this R minus can internally attack here and push away one of the ETO minus group. You will get this one. This is called acetal formation. And acetals are extremely stable with further any nucleophile attack, which means if you have any RCH with OR dash and OR dash, nucleophiles being highly negative charged, they will not be facilitated to attack on CH and remove some group out of it. So these groups will not be removed easily. Hence, this will remain stable. And once you have this stable form on hydrolysis, it will bring back the aldehydes. Okay. This we will be learning further. In fact, we have learned this earlier in reaction mechanism, but you will notice that how, in short, if at all, I have to show you the mechanism, how it happens. So any RCH, OET, and OET, if you compare, first protonation will take place, and this lone pair will drive it inside to remove this compound. So we will get this as RCH with double bond OET with plus charge and ETOH. Okay. Thereafter, on hydrolysis, this lone pair will attack here, oxygen will change to get this as RCH OH2 plus and OET. That proton will get transferred onto that other oxygen. You will get this as OH, OH and ET with plus charge. And now this lone pair will push it, remove this ethanol also. And that's how you'll end up getting an aldehyde. Okay. This is the hydrolysis of acetal groups. So that's what we have done here. This acetal on hydrolysis will give you aldehyde group. Okay. This reaction is called as Bordax-Chichibalin aldehyde synthesis. Got it? Of course, name will not be asked, but at least if it comes across the, if you come across this reaction, you should know the product ends at aldehyde. Okay. Now, there is one special case that you need to realize about Grignards is that in case if the Grignard will start becoming bulkier, if the Grignard's reagent will start becoming bulkier, it becomes difficult for it to attack on ketones. And this usually happens when you have ketones. When you have aldehydes, not so much, but ketones, if you have, this is what it will happen. So you will see, we are expecting that this CH2 minus as a nucleophile should go and attack here. So instead of doing that, now what will it do? You see the mechanism here, how it happens. Imagine I have C double bond O here like this, and then this is showing an affinity with a Grignard's reagent like this as MgBr here because it has a plus charge, and this is connected to a carbon which has negative charge, and this is connected to another carbon which is beta, and that is connected to an hydrogen here, and this hydrogen will try to connect onto this carbon here, and that's how this pi bond will become weaker. So you can notice that this is an alpha carbon, this is a beta carbon. So in case if RMGX become bulkier at beta position, and by chance if it has an beta hydrogen, then a nice cyclization is observed which will reduce this. So we will get this as carbon, making this as O minus Mgx plus, and hydrogen will come here. This we will end up getting double bond, C double bond C between alpha and beta. Okay. So this is typically how the mechanism happens. This type of a movement, this type of a pericyclic movement of hydrogen and oxygen connected to magnesium, that's what we call it as MPV reduction. So instead of actually going through this one, you would notice that this hydrogen is the one which will go all the way and gets into this formation. While this part will convert into an alkene like this. Okay, so when would this happen? If if alkyl, sorry, if Grignard's reagent is bulkier at beta positions, then you expect usually MPV to happen. Second case, enolization or acid base type of reaction. That is, if you have this ketone, now ketone is becoming bulkier. So this time this is bulkier. If you have a bulkier ketone, but at alpha position you have a hydrogen, at least one hydrogen is there. In that case, RMGX will try to take the proton from here instead of attacking as a nucleophile. So it will take a proton from here and push that negative charge into making an enolate ion. So you can see it will make into an enolate ion. And Grignard's reagent will get reduced into RH, and this will form an enolate ion. And this enolate ion, by chance, if you hydrolyze it, it will get back to the same keto form. So RCOH double bond C R and R dash, which will tautomerize to form RC double bond O CH R and R dash. Okay, now look into this. What if I take this as the reactant? If I take this as the substrate or a reactant and then perform a reaction of this RMGX with this molecule, then it has been noticed that CH3MgBr, the first favorable condition is always about doing a nucleophilic addition reaction. That means we expect this CH3MgBr to go attack onto this carbon. Thereafter, the product should be formed, which is highly anticipated. Most of the time, that is the reaction which will happen. As it starts becoming more ethyl, slowly the percentage decreases. Some percentage will convert into MPV also, which means from here at beta position, hydrogen will go and give away H minus. Same way, if the bulkiness keeps increasing, percentage of MPV starts increasing. And if the bulkiness comes to this extent, right, if it is almost like a uh, isopropyl, then attack becomes very difficult. This attack becomes very difficult. So it will only go for MPV and some percentage of enolization. If it becomes tert-butyl, that means this is bulkier as well as this is bulkier, and then enolization is most favorable. Enolization is more favorable. So have you noticed that as the bulkiness starts increasing, the reaction starts going more from NAR to MPV to enolization. Highest bulkiness means you should only think in terms of enolization. Bulkiness only on the bulkiness more on the Grignard's reagent, that means you should think about MPV. If there is no bulkiness on either of them, then NAR is more favorable. Okay, so this is the idea you should have, everybody. So please quickly check through what is MPV reduction and enolization and their percentages. Okay, have a quick look, see if you have any problem in understanding, you can discuss again. Take these basic follow-up reactions. Of course, I told you, like, if you have such bulky groups, there will not be any reaction. But in case if you have ETMGBr, in that case, the nucleophilic reactions will not be favorable, but MPV reactions can happen. That means CH2 will form here. That minus charge H minus can go here and convert that into an alkene, and this will convert into an alcohol form. So it will mostly take up that what do you say, MPV route and get this into a product. Okay, right. So these are the reactions that you need to typically learn from alkyl halides as well as the Grignard's reagent. Okay, now let's discuss about aryl halides. Aryl halides. Okay. In Aryl halides, there are three important mechanisms that we will discuss first, and then we'll see what are the application following up with that. So first one being aromatic 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 nucleophilic substitution. Aromatic nucleophilic substitution. It has various names, but mainly this is the common one which is used as the abbreviation ARSN. Okay, ARSN. The other way of representing is SN. Um, uh, I mean SNAR also, like this SNAR2 and so on, like this. Okay. There are two multiple types of reactions here. Suppose within this ARSN, within this ARSN, again we will be having a type A, which is ARSN2. Okay, or sometimes it is simply shown as SN2. Then we also have ARSN1, or simply wrote this as SN1. And then we have only ARSN given like this. Okay, sorry, or which we call it as benzyne mechanism, which we call it as benzyne mechanism. Got it? Now, this ARSN2 is also wrote as SN, which is addition elimination. And here, benzyne mechanism is basically elimination and addition. Okay. So within AR, these are the three types of nucleophilic substitutions which you will possibly see. The first of the kind we will notice is about this A, which is ARSN2 kind, or simply SNAE. AE as in nucleophilic, sorry, nucleophilic, nucleophilic substitution via addition followed by elimination. Addition followed by elimination. Okay, this is what is undergoing. Clear? For this to happen, okay, it will usually undergo only when at least one electron withdrawing group is present. It will undergo at least with electron withdrawing group is present. Clear? Right? And that too at ortho or para positions. Ortho or para positions. Let me show you with an example. Suppose if you have an halobenzene like chlorine here, this way, got it? And then I'm treating that with a nucleophile Nu. Okay, so as per mechanism, the first step is this nucleophile trying to go and attack on the delta positive charge which is present on this carbon. Got it? And that will push the electrons of pi bond here and make an accommodation for this nucleophile this way. So this is a type of intermediate which you will notice. Okay, that means this pi bond is basically shifting onto this position. Got it? So now this intermediate, because it is attacking on the chlorine, I mean carbon which has a chlorine position on it, which is kind of functional group here, right? So this is called ipso attack. The first step is ipso attack. And the first step is always the slow step here. This is the slow step of the reaction because you kind of losing out the aromaticity. Now, if you notice, of course, I need to have some withdrawing group like NO2, NO2 here. Okay. If you notice the resonating structures here, so you would see that uh, this negative charge would push here, pi bond will be pushed here, so you will get negative charge here, double bond with chlorine and nucleophile connected to N, double bond O minus with a plus charge here. So the resonance could further take place here, and that will keep moving. The resonating structures will keep happening here. So with N, O minus and O minus with plus charge, and having double bond and chlorine and nucleophile. Okay, and thereafter uh, this bond will shift here. This pi bond will go back to this position and gets negative charge on this position. Okay, and then you will get minus double bond with N, double bond O minus with plus, and here we can get chlorine and nucleophile like this. So these are all the resonating structures. And these resonating structures, if I combine all of them and convert into an hybrid form, so the hybrid form would look like this, where the negative charge is moving across the positions, having chlorine and nucleophile here and NO2 here. Correct? This this hybrid form, this hybrid form is what we call it as Mesenheimer complex. Okay, Mesenheimer complex. For our understanding, let us now use this as MH complex, just like Maharashtra. Okay, so we'll use this as MH complex. Clear? So first step is formation of this Mesenheimer complex. Okay, that will be the slow step of the reaction. And since this is the first step, what is the second step here? Once you get this Mesenheimer complex here, let me write down one of the canonical structures here like this, NO2. And now this will try to regain the aromaticity, trying to remove the chloride away. Okay, and this would be relatively faster as it is gaining the aromaticity. Hence, you will see double bonds back with nucleophile here, NO2 here, and Cl minus going out. So this is how a nucleophilic attack has been happened. Okay. Now, if you notice the rate of the reaction will be equal to some constant into substrate, which is your alkyl halide, okay, multiplied by nucleophile. So it shows that order of the reaction is 2. Correct? Here, I hope this part is understood. Then, everybody, I hope this part is clear how the mechanism happens. Right. Now let's discuss about the reactivity. Reactivity. What kind of a reactivity is observed? So, in case if you have chlorine with NO2 here, this way, and I have two more positions here, like this. And one, I'm pushing this NO2 at meta position, like this. And one, I'm pushing this NO2 at para position, like this. Correct? And one without NO2. So this is ortho, meta, para, and nothing, which we call it as hydrogen. Okay. In that case, if you follow up the rate here, so rate of reaction will be definitely more for ortho, because at ortho you will have more ability. I mean, it will help in getting more delta positive charge, and then the nucleophile can attack more easily. So you need to create that more delta positive charge so that the nucleophile can attack more easily here. Correct? So first, that is the one thing. Second is about para positioning. Okay. Third is about meta positioning. Right. So, okay, one instead of 1, 2, 3, 4, I'll write down ortho, para, meta, and hydrogen. So this will be the rate of reaction. Got it? We take this as first case. Second case. Okay. In case if you have, you know, NO2 here like this, and let's say I have all the halogens on it, including fluorine, chlorine, bromine, and iodine. In such cases, what will be the rate of reaction? Now you see rate of reaction. In such case, the rate of reaction would be based on who will have high delta positive charge first. And most importantly, what is the stability of Meisen-Hammer complex? Okay. So based on this, you will actually find that the fluorine part is more reactive than chlorine, than bromine, than iodine, which is exactly unlike the normal SN2 reaction. In normal SN2, I minus is a better leaving group that will make a faster reaction, which is not the case here. Now, why is that? Suppose if you compare the Meisen-Hammer complex here, correct? Let me copy this part. Right, check out. Stability of, sorry, rate of ARSN2 is directly proportional to stability of MH complex, isn't it? It is about MH complex stability. So if you compare the MH complex stability, you would notice that if you have, you know, let's say any halogen here and nucleophile here, and this is how the minus charge is present, correct? Now, in case if the halogen, because you need to notice one thing, this carbon is now sp3 hybridized. Because it is sp3 hybridized, there is no resonance on this carbon position. So, the stability of this Meisen-Hammer complex mainly depends upon the inductive effect of this X. So, therefore, stability of MH complex is directly proportional to inductive effect of halogen X. Therefore, fluoride will make more stable. Therefore, stability order, you will notice stability order of this Meisen-Hammer complex, correct? Stability order of this Meisen-Hammer complex. You would notice that in case if you have fluorine, chlorine, bromine, and iodine, fluorine would be better. So here you will notice that fluorine will be better than chlorine, bromine, or iodine. So this is how the stability varies. Yeah? Because of which the rate of ARSN2 will be fluoride or fluorobenzene greater than that of chlorobenzene form or bromobenzene and iodobenzene form. I guess this part is also clear. How to check out the reactivity if four different halogens are there. Now let's take up the third case. Third case is when you have more number of nitro groups. That is, if you have chlorine with one NO2 at ortho position, maybe chlorine with uh, two NO2s here like this, and then we have chlorine with three NO2 groups here like this. Okay, if this is the case, we need to check. So what do we notice? If it comes to rate of reaction, rate of ARSN2, Meisen-Hammer complex will become more stable if you have more withdrawing groups. Hence, the rate of reaction would be more for this than this. Okay, this will be the rate of ARSN2. Okay, so I hope all of you understood the mechanism and type of reactions that you will notice here? Any doubt? Let's see. Reactions of sorry, chlorobenzene, chlorobenzene derivatives. Starting with first one, if we have chlorine and then I'm treating with NaOH, I'm treating with NaOH, but this must be in a fused form. That means there is no water, correct? And the temperature and pressure that you are maintaining is extremely high, 623 kelvins, okay, which is around 270, I mean 300 degrees Celsius here, correct? And then we have 300 atm, high pressure. In such case, you will still notice the reaction would happen to get a nucleophilic substitution known as O minus and Na plus, correct? This we can still call it, we can regard this as SN2, not direct SN2, but a type of SN2 here, okay? And this is called Dow's process. Sorry, first let me finish all. Once you get this, then you hydrolyze it. On hydrolysis, you will get OH here. This is called Dow's process. This is called Dow's process, okay? So what is to be noted here is, okay, mechanism is not via ARSN2 but via benzyne mechanism or benzyne formation. Now going ahead, after some reactions, I'll show you how the benzyne mechanism works. But just remember, for this case, it is not exactly the ARSN2 type. Second, if you have a similar reaction, let me just copy this because this is the same thing which we'll be doing again and again in this case. So in case if you have one NO2 present here, correct, in that case, only the reaction conditions will be changing here. That's it, correct. What is the reaction condition this time? With NaOH, this will be 443 kelvins, 443 kelvins and 1 atm pressure. Got it? So in such case, you will get this paranitrophenol. You will get this as paranitrophenol. Third case, in case if you have two NO2 groups, one at ortho position, one at para position, NO2 here and NO2 here. Again, the reaction conditions become even milder. That means it's not too aggressive. It will become 368 kelvins, correct? And no pressure, just for normal pressure. And then we have H2O plus being done. So we'll get NO2 and NO2 here, like this. And last one, in case if you have, okay, in case if you have uh, NO2 groups at all the positions, ortho and para positions, all of them, then you don't even require NaOH at all. Here we require simply NaOH aqueous form, or simply we require warm water, H2O. That's it. That is sufficient enough to make this reaction. Okay, and that will give you direct product here with NO2 groups on ortho position and para positions. This is called as picric acid. Picric acid. Picric acid pK value is approximately 1, which means it is stronger acid than phenols, carbonic acid, and so on. So let me remind you again and again here. So check acidic strength. If you compare acidic strength, you will notice that Picric acid is more acidic than any carboxylic acids or COOH in general. It is more acidic than carbonic acid, that is H2CO3. It is more acidic than phenol. It is more acidic than water and alcohol, right? This is the acidic strength. So picric acid is quite some acidic compound here. Clear? So this is the first point you need to understand how the reaction works. Got it? Now, what was the evidence to figure out that there is a Meisen-Hammer complex actually forming? So let's see. Acha, by the way, in all of these reactions, the type of the reaction is ARSN2 only. So let me just mark it like this. All of this ARSN2, ARSN2 mechanism. Yeah. Next, notice the evidence of Meisen-Hammer complex. Eisenhower complex. Now, what is the evidence here? For example, if you have OMe here and NO2, NO2 and NO2, this type of a trinitroanisole is being taken and this is being treated with ATO minus Na plus, right? Then obviously we expect this to form a complex where we have OMe and OET, correct? But since both of them are almost of a similar nature of leaving group, that means both of them are very similar in terms of their leaving group ability. So both it can, I mean, ATO minus can also leave, or it can give you uh, ATO minus can leave, or it can leave MU minus also. So that means after the reaction here, you will notice both products will be forming. So initially, let's say we had 100% of this one. Now you would notice that both would be forming in a reasonable amount. So OET with NO2 here, NO2 and NO2 and NO2 here with benzene ring like this. This is one product and the other product is with OMe, correct? Both will be comparable amounts, comparable amounts. Hence, this can only be possible when both of them are present on the same carbon, isn't it? When their ability to relieve is almost the same. So that proves that there is a formation of Meisen-Hammer complex. Correct? This is first mechanism, everybody, how the ARSN2 type works. Okay. Now let me show you first the third mechanism, which is benzene mechanism. Then I'll show ARSN1 type. Okay. Let us see benzene mechanism. Okay. How is this operated? When it comes to benzene mechanism here, correct? So we need to check out. This is more to do with elimination first and then followed by addition. Addition type of mechanism. Okay. For example, if you have chlorobenzene here, okay. In case if you react with any nucleophile, we learned that direct reaction is not observed. Okay. There is no ARSN2 unless there is some withdrawing group. While if you react this chlorine with KNH2 soda amide or potassiumide, that in the presence of liquid ammonia, correct, then you would notice that there is a formation of NH2 product here plus Cl minus. Now, how come this is forming? Okay, now this is little because This is definitely not through ARSN2, because if ARSN2 has to happen, nucleophile has to attack, but that is not happening here. Correct? You notice that this is a reaction which is happening. Now let's try to figure out why it is happening and how it is happening. See the mechanism steps here. So first, basically, where there is chlorine, let me call this as alpha position, and adjacent to that we have a beta hydrogen also, like this. And NH2 being a very strong base, that's the important idea you should know, that it should be very strong base. Then what will it do? It will take H plus away, try to get a negative charge on the benzene. And that can actually happen because anion phenyl anion is very stable. There is no problem with that. So this anion will be formed first. And this anion will push electrons here to remove out this chloride, and thus making a intermediate which will appear like this. This is called benzene. Okay. Benzene basically, I mean structurally, if you notice, it is a benzene having these two orbitals making a pi bond here. But what are these two orbitals? These are actually sp2 and sp2 orbitals together, which are making a pi bond. Okay, this type of pi bond is being observed here. And now it is definitely not simple SN2 or not simple ARSN2, because when it comes to the reactivity order, it has been noticed that bromobenzene is relatively more reactive than that of iodobenzene, then that of chlorobenzene, and then that of fluorobenzene. Right? This is the order which has been identified. So this clearly shows that it is not ARSN2 kind. Okay. This is definitely not that similar ARSN2 type of reaction. So hence not an ARSN2 type of mechanism. So anyways, once the benzene is formed here, correct? Right. Let me actually put this at the end. Let me finish the reaction. Once you get this benzene here, so you will see on this benzene, you will see NH2 minus will attack here, pushing this bond here. Therefore, you again get a carb anion NH2 with minus charge like this. Okay. And that on reacting with liquid ammonia, it will accept the proton from it and convert that into aniline. Now you might ask, sir, why we have attacked NH2 from here? Does it make any difference attacking here or here? Well, not so much. So let me do that also. So which means in case if at all I attack the same benzene NH2 minus here and make the anion on the other side here. So I'll get this as NH2 here minus charge here like this. And that on liquid ammonia will get this aniline H. What is the difference here? See, the difference is this. Suppose if I take this carbon is isotopic. Okay, this is isotopic carbon, isotopic and isotopic carbon. In that case, on this isotopic carbon, this is the product we should expect, correct? But have you noticed that the product which you are getting is 50% of this one, approximately almost 50% of this product and 50% of this product. So that means NH2 is not exactly on the same carbon of where chlorine is going. Now, here is that position. So, the product which is formed by removing chlorine and then getting NH2, that is called ipso substitution. Ipso, that means on the same position is called ipso. And the adjacent position is called as cation substitution. So, one is called ipso substitution, other is called cation substitution. So this is an evidence that there are actually two different products forming, considering um, if the isotopic carbon is present on it. Okay. So this form of product formation is what explains that it often happens via benzene mechanism. And another evidence, experimental evidence, which you can have is this one. Reactivity order is completely different from ARSN2. Correct? Right, everybody? So please quickly go through the benzene mechanism and let me know if you have any doubt. Let me tell you about benzene. See, benzene can actually be existing in these two forms. One, like this. This is the one. And the other resonating structure is like this. Okay. So you can see because there is a triple bond on one side here. So if I compare these two canonical structures, stability of one is greater than stability of two. One is greater than two. Got it? Second thing, both are aromatic. Both are aromatic. Clear? That does not mean the benzene is stable. Correct? Benzene is unstable and it will usually, depending upon the concentration of benzene, suppose if there are less concentration, two benzenes will combine with each other to convert that into this type of addition product known as biphenylene. Biphenylene. Okay. Or if you have sufficient concentration of benzene this way, then it will become triphenylene. Okay. Like this. Like this, it will become triphenylene. Okay. One is biphenylene, the other one is triphenylene. The other reaction of benzene is that benzene can also combine with, clear, anthracene. For example, if you have anthracene, or in fact, I'm taking anthracene as an example, but it could happen with any of these groups. Suppose if you have it like this. Okay. Now notice specifically this pi bonds, these two pi bonds here, right? The highlighted ones. You can see these two pi bonds here. On these two pi bonds, it is like a conjugated diene. On a conjugated diene, if you make the benzene form, you know that pi bond will attack from here, this pi bond will attack from here, and this pi bond will shift here. And this would make, you know, a reaction like this, where we have these two pi bonds like this. And this would be on top of it, we will have one more benzene attached on it like this. This way. This is the way double bond will be present here like this. Okay. Got it? This is called Diels-Alder reaction. We have come across this before. Diels-Alder reaction. Diels-Alder reaction. Okay. So these are the byproducts which you can get from benzene. Clear with this point now? I hope all of you understood what is the importance of this reactions. Okay. Now, as much as the benzene structure is, I mean, benzene form is concerned, not a lot of reactions will be asked here. Okay. I mean, because this is not a part of JEE syllabus. They have deleted, I mean, this is a deleted syllabus. Usually this benzene cases are not usually asked. So I'm not going too much detail into that benzyne form. Okay, right. This is the benzyne mechanism. So, just as to show the examples, correct? In case if at all we see such strong reactions, some examples, sorry, examples, the strong basis, then how the reactions will take place. Check it out. Suppose if you have it like this, where you have, uh, let's say, chlorobenzene here, correct? Like this. And no, no, yeah, chlorobenzene. And then you are treating this with NaOH fused, NaOH fused with high temperature and pressure. In that case, we learned that you will get this as O minus and Na plus. This happens to go via benzyne mechanism. This happens to go via benzyne mechanism, and this is called Dow's process. So the mechanism is pretty much the same here. Suppose if there is a chlorine and hydrogen here, so OH minus in such a fused form will act like a strong base, attacks here, pushes here, removes Cl here. I'm directly writing the steps here now. So you can see a benzyne getting formed here, and thereafter again OH minus will attack back here. So you will get this as a minus form, and you will have OH with minus, and internally that will take H plus and convert into O minus and H here like this. So that's the Dow's process. Okay, like this. Where are the other examples you will notice is this one. When you have chloro and reacting with ammonia, but in the presence of CuX, some cupric salt, and strong heating. In such case, this ammonia will now become a stronger base, converts into NH2. Similarly, if you have KCN in the presence of CuCN and strong heating, then also it will start converting into CN via benzyne mechanism. And in case if you have something like an N2 plus group, which is a strong leaving group, and then you have COO minus, which is also a good leaving group on heating. Now, what would happen here? See, first we have N2 plus, which is very easy leaving group. Carbon dioxide will leave, okay, by making that minus charge on the benzene. This pushes and relieves N2, and that's how you can get benzyne form here as well. Correct? Well, after this, it can get into biphenyl, triphenylene, or any other reactions. But this is the benzyne as the intermediate which is formed. Correct? So these type of reactions are usually expected out of benzyne mechanism. Clear, everyone? Now, let's see the B part of the reaction, which is about SN1 type, or in short, it is written as AR SN1 mechanism. Now, let's see when will this happen. ARSN1 means we expect the carbocation to be formed. Okay, to be fair, suppose if you have a benzene and treat that with concentrated HNO3 in the presence of concentrated H2SO4, we know that this will give nitrobenzene. Correct? We get this as nitrobenzene. And this nitrobenzene, when you react with tin and HCl, it will convert into aniline, which is NH2. It will convert into aniline. And aniline, when you react with HNO2, that's when it converts into something called diazonium ion. Okay. And this will always have a chlorine with it. So that's why it is called benzene diazonium chloride. So industrially, we call this as BDC, benzene diazonium chloride. Okay. Now let's see this last step, how the reaction is happening. Okay. So when you take NaNO2 and react with HCl. It will form HNO2 plus NaCl. And HNO2 structurally, if you notice, it is like this. And since it is in acidic medium, the lone pair will take H plus, convert into H2O and double bond O plus, and H2O will relieve to convert into H2O plus NO and double bond O plus. So this is how an electrophile is generated. This is electrophile. Okay. And once you get an electrophile, aniline NH2 will react with N double bond O plus and convert this into N, H and H with N double bond O plus. And see this, slowly these two hydrogens and oxygen will start combining with each other and try to relieve itself as H2O, and hence making this as N triple bond N plus. And since it is in a medium of HCl, you will have chloride present on it and you can crystallize this. Now, this is stable under 5 degrees Celsius only. This will not be stable over 5 degrees Celsius. Got it? So as long as 0 to 4, 0 to 4 degrees, I'll say, because otherwise it will be crystallizing as. So 0 degrees to 5 degrees Celsius. This is where it will be more stable and you can keep that for a longer time. Now, what happens if you see the mechanism? First, we have made a diazonium salt formation. Now, it is the diazonium salt formation which will make the reactions to happen. So, see the type of reactions, what they will do. First reaction. Now, when you have N2 plus present and then a nucleophile is approaching, in such case, we can expect this to relieve the N2 plus first, which is the rate determining step, just like SN1, where carbocation is the rate determining step. And thereafter, nucleophile will attack. So, in the first step, it is not attacking. In the second step, the nucleophile will attack and thus gaining this product, right? So, this is formation of carbocation, right? So, this is phenyl carbocation. Although phenyl carbocation is unstable, still this is going to be formed. Okay, clear? So why this is happening? You know that N2 is an extremely good leaving group. That's why it will easily leave away this position. Got it? Now, what is the evidence of that? See, evidence of, carbocation. That is, it is going via ARSN2. How do we prove that? See, in case if you have N triple bond N with a plus charge here, and let's say we make this oxygen, this nitrogen as isotopic nitrogen, then what has been noticed is that, just on slightly heating, very mild heating here, so you will get a positive charge here with N triple bond N, right? And this is that isotopic nitrogen. And slowly, because you are hitting it very mildly, you will see this nitrogen can again attack back with this plus charge, but this time this is that isotopic nitrogen. So you can see it is actually swinging between the two forms of nitrogen, two ends of the nitrogen. And if two ends of the nitrogen are connecting, which means it has to go through this carbocation formation only. So that's the evidence that there is a carbocation actually forming here. Correct? Now let's see the examples where the examples of ARSN one type of reactions. So first one is when you have diazonium salt formation, diazonium salt present, and then you react with water slightly warm. Okay. So when you react with water, it will go through that carbocation formation first, and then H2O will attack on it thus giving an phenol as a product plus N2. Phenol will come out as a product, and H plus which is released will become HCl, because diazonium salt will always be coming up with Cl minus like this. This is the product formation. Got it? Next, second reaction where this will happen is known as Boltzmann reaction. Boltzmann reaction, right? When it comes to Boltzmann reaction, you will notice that we have N2 plus and Cl minus. This, as you react with, uh, NaBF4 like this, a salt form, correct? Then first the chlorine will get replaced here. Okay, in this salt you'll get N2 plus and BF4 minus will be formed and NaCl be out. Okay, and now when you have this compound on heating, correct, you will start gaining this into carbocation first with N2, and okay, then we get BF3, correct, and F minus. Yeah, I'll give it. So then you will have a carbocation that reacts with F minus, attacks on it, and you will get this as a fluorobenzene. Okay, so Boltzmann reaction is a preparation of fluorobenzene. Got it? I guess this reaction is clear, everybody. Okay. One more reaction where ArSN2 is observed is when you have aqueous Ki. Okay, aqueous Ki reaction. That is, if you have N2 plus Cl minus reacting with aqueous Ki, again it can form a carbocation, and then the I minus can go and attack on it, thus giving iodobenzene. These three are the reactions. These are the only reactions, by the way, where ArSN1 is observed. Otherwise, in generally, ArSN1 reaction is not usually observed. Clear? I suppose all of you understood the mechanisms. Yeah. These are the three main mechanisms of this topic. Okay. Now let's get into the preparation of aryl halides. Preparation of aryl halides. Okay. So first one is basic halogenation. Okay. So when it comes to halogenation of benzene, you'll see if you react benzene, correct, with either X2 in Fe, correct, or X2 in FeX3, or X2 in AlCl3, correct, where X is chlorine or bromine, then you will definitely get this as halobenzene via EAS mechanism. Via EAS. EAS we have learned in benzene, so I'm sure you can relate it. Correct? Similarly, if you have benzene and if you treat this with I2, okay, but this I2 has to be present with some oxidizing agent. In that case, we can get iodine here. Correct? This is the reaction that will take place. But oxidizing agents has to be any one of them, HNO3 or HiO3 or HGO. This also we have learned it, that any of these can be acting like an oxidizing agent, and that will help in making this reaction. Got it? Second, we learned Hans-Decker reaction already. Hans-Decker reaction. So where we take a silver salt of carboxylate, so COOAg, and then treat that with Br2 in the presence of light or heat, right? So in that case, we will get this into X here, in this case bromine plus AgBr plus CO2. So you might wonder, sir, is it only for bromine? Not necessarily. Any X2 where X is chlorine, bromine or iodine, like this, plus AgX plus CO2. Done. This is Hans-Decker reaction. Got it? Next, using diazonium salts. Diazonium salts. Okay. For diazonium salts, we have to directly remember the reactions, everybody. I'll directly give you like a uh, I'll directly give you like a table here. So please check. So if you have N2 plus and then you react this with CuX in the presence of HX, correct? CuX in the presence of HX or only CuX. We can write it as or HX, correct? In such case, you would notice that we will get this as, don't write or here, just write CuX. That's easier to analyze. So here we have Cl minus, benzene diazonium chloride. In that case, we will get this as X here and N2 plus uh, CuCl. This is a product form. Okay. This X could be chlorine, bromine, or cyanide. Okay. And the name of the reaction is Sandmeyer reaction. Sandmeyer reaction. Correct. I'll give the mechanism. First, let me write down the entire terms here. So, second reaction is with, HX with copper dust. So, take the crystals of copper, I mean, powdered copper here and add with HX. Then also we'll get this as X plus N2 plus this as C plus this as HCl here. This is called as Gattermann reaction. Gattermann reaction. Next one, in case if you react with NaBF4, okay, or HBF4, you can also use this as HBF4 directly. So first you will get something like a salt form, N2 plus BF4 minus, and that on heating will convert into fluorobenzene. We just learned that. This is called Ball-Schiemann reaction. Ball-Schiemann reaction. Okay. The other reactions, actually this will be more relevant going ahead, but just I'm writing it for the sake of understanding here. H3PO2, if you react followed by water, first and second, like this, if that is given, it will become H here. That means you will get benzene and H3PO3. The same reaction will happen even with ethanol also. If you take ethanol, you will get benzene plus CH3CHO. All right, benzene and CH3CHO. And lastly, with water, warm water, H2O and warm water, we have just noticed that it will become phenol, right? So these are important reactions from diazonium salt, at least for this topic. Okay. Now, what is the type of mechanism that happens? See, let me just write down that here. Sandmeyer reaction happens via SET mechanism. SET. Here it is AR SN1. This is AR SN1, while these two are also SET mechanism. What is SET mechanism? SET means single electron transfer. SET, which is called single electron transfer. So single electron transfer basically means a radical mechanism. Okay, so it is happening via radical mechanism. So you see how the reaction takes place. First, let me explain through Sandmeyer's reaction. So if you have pH N2 plus Cl minus, this is the disonium chloride salt, and that when you react with, let's say, HX, okay, then we can know that it will become pH N2 plus and X minus plus HX. This is the first step. And then pH N2 plus and X minus when you react with CuX. Okay. See, sometimes the first step is not given. I'm just taking it as a caution step. You can directly start with the second step also. So this, if you react with CuX, this will become pH dot, a radical, and then copper will become CuX2, and then N2 gas will be lost. So basically copper got oxidized and phenyl got reduced here. Got it? And once you get that here, so now as a radical what we have here, so this pH dot which you have, that again reacts with CuX2, converting this into PHX plus CuX. So you could imagine like this, as if we have CuX and X with pH dot. So this pH dot and this X dot are combining with each other, and that is releasing CuX, and here you will getting PHX. That's how you will get halobenzene or cyanobenzene or chlorobenzene, bromobenzene, anything of that sort. This is, SEN mechanism. I hope this compound is clear, everybody. Okay. Right. See, this or here I have to write the alternative reaction also. This or sometimes it is used HPTF6. That will also give you the same type of reaction. So basically you will get this as uh, fluorobenzene here. Okay, with heat. Right. So this is the single step mechanism here. Got it? Now notice these are all the preparation reactions of aryl halides. Next, see. Next, let us see about the physical properties. Physical properties of aryl halides. Okay. So first one, if you notice by structure, if you have CH3, CH2, and then Cl. Okay. Let us call this as length A. And then we have CH2 double bond CHCl. Let us call this as length B. And then you have benzene, where you have like this with this one Cl. Let us call this as length C. So if you compare the bond length of carbon and chlorine in these three, A definitely is longer, and then between B and C there is a back bond. I mean there is a resonance which is happening here. But the resonance will be way more effective in allyl as compared to that of benzyl. Okay, because benzyl already has its own aromatic resonance. So getting one more lone pair from this chlorine will be slightly weaker. So therefore we can say A is greater than C greater than B. This is the bond length form. So this is the first thing we should know. Okay. Second thing, when it comes to dipole moment. Dipole moment. In the case of dipole moment, you will only see the mu values being ortho greater than meta greater than para wherever you have a dihalides. So that means Cl and Cl Of course, this will have, you know, bond angle, I mean the dipole angle at 60 degrees. This will be at 180, 120 degrees, and at para position it will be, or the meta para, it will be at 180 degrees. This will be the dipole moment, right? Third one is about melting point and boiling point. Okay, so in this case you will notice that when it comes to melting point, obviously the geometry and how well it is stacked, how uh, symmetrical it looks like, that makes more sense. So you will see uh, para is greater than, right, para is greater than, um, ortho is greater than meta. Okay, between ortho and meta, it is the dipole moment which will cause a little bit bigger better edge here. So this is all about the effective packing that a para is giving. Okay, clear. This is about melting point. When it comes to boiling point, now this is very interesting. In the case of boiling point, usually we always rely on dipole moment. It will always go in terms of dipole moment. But here you will notice that the ortho is definitely more in dipole moment. But then comes para. It is an exceptional form. So then comes meta. So here, this is an important exception you should remember. And in which case you will notice here, well, the data is available for dichlorobenzene and dibromobenzene. For both these cases, you will always remember ortho greater than para greater than meta. It's not meta that comes before, but it is ortho. Okay. So I suppose this is clear. These are all the physical aspects of aryl halides. Now let's see chemical reactions. Since we already know the mechanisms, now we'll quickly go through the reactions directly. Okay. So first is nucleophilic reactions. Sorry, substitution. Nucleophilic substitution reactions. Okay. So starting with first, in case if you have a chlorine here, NO2 here, definitely this will help for nucleophilic substitution. So if you have ETO minus Na plus, then chlorine will be replaced by OET and NO2 will come here. So this is the product formation. Okay. In case if you have two nitro groups, so Cl and NO2 reacting with MES minus Na plus. This is also a very basic ARSN2 type of mechanism. SME, NO2 and NO2. This is the product. Third one, okay. In case if you have, you know, chlorine here, fluorine here, and NO2 here, and then I'm treating this with MES minus Na plus. Now notice, although fluorine is a better reacting group, problem here is chlorine can do this better reaction because NO2 which is present here right now is ortho to chlorine. That's why it is the chlorine which will relieve first here. So you'll get SME, fluorine will remain, and you'll get this as NO2. Of course, I'm taking only one equivalent. In that case, this is the product you will get. Here, everybody. So I'm sure you do remember this part. Okay. Similarly, if you have chlorine here and then you react with NH3, Cu2O and heat. Just now I told you that this will take the route of benzene mechanism and gets into NH2 form. But if the question is given only as NH3, then you say no reaction, no such reaction will take place. On the similar lines, if you have chlorine and treat that with CuCN and heat strongly, even if you heat strongly, it will go via benzene mechanism and get you through this one. So via benzene mechanism. Yeah, got it? Now, second, reaction with metals. Reaction with metals. This we have done it before, right? It's just repeat reactions. That is, first, if you have chlorobenzene and react with sodium in the presence of ether, imagine taking 2 moles of it. So you will get two benzene rings connected with each other like this, correct? And this will become biphenyl plus 2 moles of NaCl. What do you call this reaction? Fatigue reaction. Fatigue reaction, correct? In case if you have chlorobenzene with CH3Cl and that in the presence of ether, then you will get toluene plus NaCl, and we call this as Wood's fatigue reaction. Wood's fatigue reaction. Next, in case if you have any halogen here like this, and then you react with Cu, correct? If you directly react with Cu, right? In that case, it is called as, here also the coupling will happen like this. The same coupling product you will get, and you'll get this as CuX. This is known as Ullmann's reaction. Okay, usually it is done more by iodides, but even if you have other chlorides also, you'll get the same thing here. Okay, next, in case if you have chlorobenzene plus lithium in ether, lithium does not make anything of this sort. Basically, lithium will just simply, sorry, one lithium. It will simply give away electrons and get minus charge here and combine that with lithium. So this will be stronger bond here, plus X minus will leave. Got it? So this will be organo metallic bond. Okay? Highly, I mean, sufficiently covalent. It is sufficiently covalent in nature. Okay? I just written it as minus and plus, but it is not exactly minus and plus. There will be a bond on it. Okay? So on this regard, there is a special reaction known as okay, metallation. Trans transmetallation. So wherever you see any wherever you see like this, where you have any halobenzene and then you react with CH3Li. So wherever you see CH3Li or RLi, okay, clear. In that case, you will notice that first this CH3 minus will actually attack on X rather than that of benzene. And now you will get that as minus charge on benzene, correct? Like this. And this will become CH3X and then lithium plus. Got it? So because this bond will break onto this side. And now this minus will combine with lithium. And that's how you will get lithium bond with benzene. This is a product you will report. Okay. Why is this happening is the driving force here. The driving force of pH minus, stability force is stability of pH minus greater than that of CH3 minus. Okay. So that's the reason why this transmetallation will happen. Clear, everyone? This is about reactions with metals. Okay. Grignard's reagent is anyway the case which we have learned earlier. So you can see, I can just repeat it again. So any halogen, when you react with magnesium in the presence of ether, correct? So then you will get this as minus here and sorry, overall minus here and mgx plus here, like this. Grignard's reagent will form, and you know that Grignard's reagent reactions, how they happen, we know that, correct? Next, see the third set of reaction. This is about electrophilic electrophilic aromatic substitution. EA's reactions of aryl halides. Okay, you know that on aryl halides, all X groups here are X is electron withdrawing group on benzene, but OP directing for electrophiles. OP directing for electrophiles. So if an electrophile will come, it will always take it at ortho position or para position. Okay. And that's what I'm trying to explain here. So if you have X here, correct? And if you react with Cl2 in the presence of Fe, correct? So in that case, you will get two products, X with Cl here and X with Cl here. Generally, para is always major in these cases. Para is always major in this case. So see the next reaction. Friedel-Crafts alkylation, that is CH3Cl in the presence of AlCl3, that will also give you ortho product and para product. And which is major? Para is major here. Sorry, in the same thing. If you have CH3COCl in the presence of AlCl3, this is Friedel-Crafts acylation X, and C double bond O CH3, this is ortho product, and X with C double bond O CH3, this is major. Okay, so this is Friedel-Crafts alkylation, and this is Friedel-Crafts acylation. Okay, see the next reaction. Okay, the next important reaction is this one, where chlorobenzene is reacting with CCl3CHO. Okay, trichloroacetaldehyde. Got it? Now, if you react with this one in the presence of H plus, to make this complete reaction, we require 2 moles of this chloro, and this will end up getting as CH3CCl3CH with benzene rings connected like this. So chlorobenzenes will be connected like this at 2 positions. Correct. So if you notice the mechanism, so you will see this as CCl3 C double bond OH in acidic medium. So the lone pair present on this oxygen will attack on this H plus, and that will make it CCl3 C double bond OH plus this way. Okay, this is the first step. And now this carbon is sufficiently positive, so that makes it highly electrophilic. Hence, if you have a chlorobenzene from the para position, it will go and attack on that carbon. So from this position, it will attack here. This bond will move, and that will make the first substitution. So we'll have this is chlorine with CHOH and CCl3. This is the first product form. But since it is still in acidic medium, okay, still it is in acidic medium. So with protonation, it will get protonated to get this as OCH2 plus. And this, if you react with chlorobenzene again, from this para position, it will attack, remove out this water. And hence, we will get this as chlorobenzene on one end, CHCCl3 on the other hand, and this side also you will have another chlorobenzene here. This is the product. Okay, this is read as dichloro, dichloro, diphenyl, dichloro, diphenyl, trichloro, trichloro, ethane, trichloroethane. So you can see the wording here: dichloro, diphenyl, and trichloro. So that's why this is called DDT as common name. Okay, this is called DDT as common name. Clear? And its IUPAC name, sometimes that would be usually asked here, correct? So that will be 2,2 bis 4 chloro 4 chlorophenyl 4 chlorophenyl, and then 1 comma 1 comma 1 trichloroethane. This is a product formation. Okay, so everybody quickly see the electrophilic reactions once. If you have any doubt, you can ask me. Okay, please check. Test of distinguishing okay, RX and RX and ARX. So that is, in case if you have halogen like this, best thing is to do is take aqueous AgNO3, correct? In aqueous AgNO3, this would form OH here, and then AgX gets precipitated. Okay. While the same reaction, if you do it with other side where you have benzene, such type of reaction will not take place. So you will not get any of this product formation. So no reaction here. So if there is no reaction happening with AgNO3, definitely that is going to be an aryl group. If it is happening, it has to be a simple alkyl group. I suppose this part is clear, right? Right. So the last thing we need to learn about in this topic is about polyhalogens. Polyhalogens. Okay. So I think polyhalogens will do one thing, because it will have one very important mechanism known as the haloform reaction, which will be a part of alkyl halide, aldehyde, as well as ketone. So it will be observed in all the reaction sets. Okay. So therefore, it's better that we discuss it in the next class thoroughly. Got it? And that's a very crucial reaction. And that will end up with this topic. And then we can continue the discussion of the alcohols also. Clear? Okay, guys. So we'll end up here now.